Hi everyone. This is the SEBA tutorial at ONF Connect 2019. I hope everyone has gotten themselves situated. I'm Zach Williams. I work for ONF, and I'm going to go over sort of the structure of what's going on today, and then I'm going to pass this on to Scott Baker and Andy Bavier, who are going to do the first session. So to give you guys an idea of what's going on, this is a fairly hands-on tutorial, but there's also a lot of slides. So we've structured this tutorial to work well for both people who are technical and non-technical, but we're going to be doing a fairly technical deep dive. It's just so you guys know, it's a lot of cutting and pasting and looking through, and running sort of the command line and the GUI interfaces of SEBA. So you should be able to follow along even if you're not very technical. But we'd really like, we'll be in the room to help, and we really want people to be successful with that. So to give an idea of what's going on during this session, the first session is from 9 to 10:30. We're going to give a big picture overview of PON networking in SEBA, and sort of where we see SEBA and VOLTHA positioned in the ecosystem. And then we're going to be setting up SEBA-in-a-Box, which is a virtualized version of SEBA that people can use to see and explore the system and do development on. The second session is 11 to 12:30. We're going to go over the community, all the partners and people who are working on SEBA and contributing to both SEBA and VOLTHA. Then we're going to go through a lot of the operational aspects of using the pod, using that SEBA-in-a-Box we set up in session 1. And then that's going to be part of the lab, which we're going to explore and operate it. The third session, we're going to go over operator workflows and FCAPs. So different operators have different workflows that they need because their networks differ. And FCAPs is, deals with sort of a lot of the management capabilities that exist in SEBA. And then we're going to go through those both in the lab. And then the last session from 3:30 to 5, we're going to go through the development loop. You're going to see replacing an actual component in the SEBA system and how quick the development process is for making changes and getting those changes through our system. We're going to go over how SEBA is tested, and then at 4:30 we're going to Saurav is going to drop in, and he's going to give some information about the roadmap and operator trials and some of the new functionality that is coming to SEBA soon, like the virtualized BNG. And with that, I'm going to turn this over to Scott Baker. He's going to go over the first section, which is the overview of SEBA and PON networking. So thank you, Scott.
Thank you, Zach. Okay, so I'm going to give a brief overview of SEBA and PON networking to sort of set the basic concepts that we'll be going through today. In this session, we're going to be looking at what are the parts of a PON network? What is VOLTHA? That's one of our key components, and how does VOLTHA abstract the PON network? How is a SEBA profile launched on the Cord platform with Kubernetes and Helm charts? And what is SEBA in a box, and why is it useful? And these will be done both through slides as well as an extensive hands-on portion. So traditional fiber to the home residential access. We've got a picture of the traditional solution here. Working from left to right, the customer will have a residential gateway and an optical network unit. The ONU will be responsible for taking stuff off of Ethernet and putting it onto a passive optical network. So let me try my pointer here. Down there between the two, that's the passive optical network between the residence and the central office. Inside of the central office, you have an optical line termination that takes the optical network and puts it back into Ethernet, also doing typically a bunch of processing on the packets. You'll have an aggregation switch, which may aggregate multiple OLTs traffic, and then it puts it out on a broadband network gateway, and the broadband network gateway will put those packets out on the internet. And of course, the reverse just flows in the opposite direction. Now, each device in this traditional solution is a closed proprietary device. It's not programmable, and this represents a lot of capex and opex to the operator because they have to buy these devices from certain vendors. It also represents a lack of agility because they cannot deploy new innovative technologies rapidly because of the closed and non-programmable nature of these devices. So what we saw where we were excited was to be able to bring SDN to this, to disaggregate these fixed closed devices into a combination of hardware, because certainly there's some hardware necessary to terminate an optical connection, but also software that will manage that hardware and be agile and allow new innovative technologies to be developed. And we've called our project CORD, which stands for Central Office Rearchitected as Datacenter. And one of the key things about CORD is it's meant to serve many different purposes. So we can see 3 different use cases up there. There's a residential use case, that was the fiber to the home that we just showed on the previous slide. There's also mobile use cases, so for example 5G stuff, and then there's enterprise use cases. And we see those as all being able to work on the same platform. So we develop one platform that sits in the middle that will provide the management and abstraction solutions to use Whitebox hardware. And the Whitebox hardware will reduce the capex and opex. Down here we have Whitebox compute devices, just commodity servers. We have OLTs that may be Whitebox or they may be vendor OLTs. We can use either one. And by separating out the software from the hardware, we see this as a way to drastically reduce the cost while improving the agility. We see this as bringing the best of cloud, network function virtualization, and SDN together. And it will allow us to achieve the economies of a data center and the agility of a cloud provider while still serving all of those solutions that we needed to serve up at the top. So what we're going to do is we're going to work through this traditional fiber to the home, and we're going to knock down these proprietary boxes one at a time. So the first box that we are knocking down is this one over here, which was the proprietary OLT, and we're going to separate it into 2 parts. One is the hardware necessary to terminate the optical connection. That'll be a Whitebox OLT, and the other will be a software stack that we will call VOLTHA. And VOLTHA is going to present a virtual OLT abstraction that will abstract this PON and allow it to be managed by our SDN controller. So let's talk about how we're going to disaggregate this. So over here on the left, you have a traditional OLT. It's a large proprietary box. It has many multiple blades in it. You'll see there are blades here, a whole pile of them that do the actual optical termination. They will have passive optical connections in the front, and then there are blades, so out the back they will hook to some kind of backplane that sends traffic to other components in this OLT. You'll also have a bunch of compute blades that will do the packet processing on those packets. You will have some software in there that implements higher level functions like VLAN abstractions, IGMP, authentication, multicast. There's a backplane, a proprietary backplane that will connect all of these blades together. And there is a management system that will allow the operator to manage this thing, typically through another proprietary API. So how are we going to take this and SDNize it into a disaggregated solution? Well, the first thing we're going to do is we're going to take these proprietary optical termination blades, and we're going to use some Whitebox OLTs down here. That will handle the actual optical termination, so the OLT. On the front, there will be a bunch of transceivers with optical connections, and on the back, some number of Ethernet ports come out. Oops. And then we're going to run our software stack that manages that abstraction. So our software VOLTHA, we'll be talking about that quite a bit here. And VOLTHA is going to implement a bunch of abstractions on top of that OLT. So it will implement an OMCI stack, it will implement an API, and VOLTHA's northbound is going to speak OpenFlow and netconf to make this VOLTHA look kind of like a switch. And things that look like switches, we can run another one of our software products called ONOS. It knows how to manage switches. We make the PON look like a switch, and ONOS will be able to program that PON using traditional OpenFlow type flow tables. And then on top of this, ONOS will run a variety of apps that will serve such things as the VLAN abstraction, authentication, multicast, et cetera. ONF has worked extensively along with our partners and community members developing VOLTHA as well as ONOS, so we're working hard on those software solutions. The VOLTHA Architecture. So we've tried to modularize VOLTHA because we want it to be able to abstract a large variety of OLT hardware. So it can work with both vendor-specific OLTs over here, be it via vendor-specific adapters, and it can also work with an OpenOLT adapter that we have developed, and together with EdgeCore, a Whitebox OLT of theirs, as well as many other people are now working with the OpenOLT adapter. And then we also have an ONU, ONT abstraction, and we have ONU and ONT adapters that will allow various vendor ONUs and ONTs to be plugged into VOLTHA. Above that, you have kind of a VOLTHA core, which is going to handle a bunch of the processing responsibilities inside of VOLTHA, so configuring it, logging an OpenOMCI stack, stuff like that. Tech profiles to configure the technology, and various interface technologies on the top, so a REST agent as well as an OpenFlow agent, a netconf agent, et cetera. I'm going to walk through a quick example of how the hardware and software comes up. If you could imagine, we have an OLT that has just been added. We've also got VOLTHA and ONOS running. VOLTHA will activate the OLT, and the OLT has some ports on it. It has NNI ports. Those are the Ethernet ports, and it has PON ports on the other side. So it's got 4 NNIs and 2 PON ports. And it's going to respond to VOLTHA and let it know about its configuration. And VOLTHA will build an abstraction of the OLT that includes just the NNI ports. So you can see it's taken the 4 NNI ports from there, and it's built this logical switch abstraction here that also has 4 NNI ports. And then it will inform ONOS because VOLTHA says, hey, I have a new switch. ONOS says, you know, I understand switches. So ONOS will be aware of the switch. Now let's say an ONU comes up. The ONU is attached via the passive optical network to the OLT. The ONU has a UNI, so there will be some negotiation when the ONU comes up to activate it. And that UNI port will be added to the logical switch abstraction here. So now the logical switch has 4 NNIs and 1 UNI. All of this passive optical network detail here has been hidden from that logical switch abstraction. So we will tell ONOS about that. A second UNI, if it comes up, or a second ONU, it will have its own UNI. It will be connected, it could be via a separate PON port, or it could be via a passive splitter. You can have many ONUs down there on the OLT. But that second UNI comes up and is realized as a second UNI port on the logical switch. So now our logical switch abstraction has 4 NNIs and 2 UNIs on it. And ONOS, again, understands switches and can program flows to that logical switch abstraction. So on top of ONOS, we will run a variety of ONOS apps. These apps will do things such as implement a VLAN abstraction. We will do DHCP trapping. We can implement multicast, authentication, stuff like that. The next piece of the architecture over, we also have a switch, because all of these OLTs are typically behind an Ethernet switch of some sort, which is going to aggregate multiple OLTs together and then connect them to the BNG. So the switching fabric, it's a switch. ONOS will also manage that switching fabric. And we will run various bridging and routing apps in ONOS to manage that switch. So what we have done is we have developed, together with our partners and community members, the first industry first Whitebox XGS-PON OLT. It uses open hardware specifications from the Open Compute project and open source software from ONF and Open Compute project. Here is a picture of one of the EdgeCore Whitebox OLTs. You're kind of looking at it top down. I don't know if we actually have one of these on the show floor. Sometimes we have them by our demo booths. You'll be able to look into it if there is one, but they're kind of interesting to look at. And just to see kind of how these components are broken up here, on the OLT, there is some software running. So the OLT comes with a built-in SDK, a BAL, which is a Broadcom API, and some other SDK type stuff inside of it. And then there's this OpenOLT driver and agent, which speaks the OpenOLT abstraction. And then that will speak to the OpenOLT adapter within VOLTHA. And ONF has worked on both of those components. We've been heavily involved with the OpenOLT driver as well as the adapter. And why use an OpenOLT adapter? Why not just develop your own adapters? Well, one of the reasons for this is that it eases adoption of new vendors. So we have provided a reference OpenOLT agent to run on the OLT. We have provided the adapter already in VOLTHA. A new vendor who wants to come online quickly can either start from our agent or write their own lightweight agent, speaking this gRPC protocol to the OpenOLT adapter, and they can get their hardware adapted quickly. This includes Whitebox vendors. And we have several different people who have been working with OpenOLT. So down here we can see there are a variety of OLT manufacturers. There's CIG, EdgeCore, Iskratel, Tellabs are all working with OpenOLT. And we also have an OpenOMCI specification, and we have multiple vendors working with OpenOMCI on their ONUs over here. So for example, we have Alpha, Iskratel, Arcadian, CIG, Tellabs, and we're always interested in bringing more people in on these OpenOLT and OpenOMCI. So we have knocked down the first box here already by bringing out VOLTHA and disaggregating that proprietary closed OLT into a Whitebox OLT plus software solution. Now we're going to knock down the next box in the fiber to the home by coming out with, instead of a proprietary aggregation switch, we'll use Whitebox switches together with a switching fabric developed in ONF called Trellis. So Trellis, this picture is going to look a lot like the VOLTHA picture because we've taken the same concepts and applied them to switching. So we're going to use open hardware specifications for the switches together with open software developed by ONF and OCP, and disaggregate that component. So here is an example switch. And you can see the components are kind of broken down in a similar manner. Whereas before we had VOLTHA running over here, now we've got the SDN controller running Trellis apps, and there is an OpenFlow agent running on the bare metal switch, as well as the various SDKs and APIs and stuff that run in the switch, and the Broadcom ASIC and other components that go inside of it. We will maybe talk about Trellis briefly today, but there will be, throughout the conference, I think there will be some Trellis presentations if you're interested. So Trellis knocked down the second one of these blocks. We've still got the third block, which was the BNG. That is a closed proprietary component. As of today, we are still using external BNGs, but we are rapidly adopting an effort to disaggregate the BNG as well and to move that into a commodity hardware plus software solution. And we will talk about that briefly at the very end of the day in our roadmap moving forward. There will be a presentation on how the BNG is being disaggregated. So anyone who wishes to learn more about that, please stay for that roadmap at the end of the day. So I'm going to go through 3 different architectural diagrams. This one here is going to kind of give you an idea of how the hardware and software fits together. So we have over here at the side, we have the customers with their ONUs. They're connected to a PON, it's passive optical splitter there, and connected to an OLT. There may be many OLTs. Those OLTs are all connected to some switches. Here we can see 2 switches for redundancy for all of those OLTs in a fabric. We can do with Trellis, we can do leaf spine fabrics, all sorts of stuff like that. And then out here to the external BNG. And as I said before, we're working on moving that BNG internal. That's will be talked about at the end of the day. And we also, hanging off the switches, we have a bunch of servers. And these servers are commodity servers where we will run our software. So VOLTHA, for example, runs on those servers. ONOS can run on those servers. Something we call the NEM and other services will be able to run on those servers. So now how these things are connected to the software components. So you can see VOLTHA is managing these OLTs. ONOS is managing VOLTHA. ONOS is also managing the switches. And on top of ONOS, we're running various apps. At the very top of this, we have something called the Network Edge Mediator. And the Network Edge Mediator is there to provide a unified abstraction of this pod to the various operators, so that the operators don't have to deal with all of these components individually. It's sort of the fill the gap component. We're going to be talking a lot about the NEM throughout the day today in the tutorial, so you'll learn a lot about it. But on top of the NEM, for example, we have had an abstract OLT abstraction deployed together with ONAP. Some people at the AT&T Foundry worked on that. And also other operators can come with their OSS and BSS and speak to the NEM API, because it is sort of a unifying common abstraction, and be able to manage the pod through the NEM. Now, throughout this, we've been using best practices of cloud computing. So we're heavily invested in containerizing our software for modularity, and we're heavily invested in using traditional open source tools, such as the Docker, Kubernetes, and Helm stack of software to manage the pod. So that was the first way of looking at this. A slightly different way to slice it is by the projects at ONF. And ONF is involved in many different projects throughout this space. We can see at the top there were those three familiar use cases: the residential, enterprise, and mobile. You've got the NEM, that interfacing gap layer in the middle. Trellis for handling the fabric. ONOS as the SDN controller. Then we've got VOLTHA Stratum for managing P4 switches. SD-RAN for the radios, ODTN. And if we want to look at what parts of these comprise SEBA, it's these ones here in the middle: the NEM, Trellis, ONOS, and VOLTHA, that we will be diving into a lot during today's sessions. Now, a final way to look at this is sort of this software architecture platform way of slicing it. And I've got this broken up into three different layers. Each layer sort of builds upon the ones below it. So down here at the bottom, you've got a platform layer. Inside of it, you will have logging and monitoring components. These are all kind of infrastructure-ish things, like Elasticsearch, Kibana, Prometheus, Grafana, so various monitoring tools that implement our FCAP solution. On top of the platform runs a profile. You can eventually, or maybe even now, operate multiple profiles, and each type of access hardware would be a different type of profile. So for example, there could be a residential profile, a mobile profile. In enterprise profile, you could bring up just one of them or some combination of them. The profile we'll be doing today will be the SEBA profile. And the SEBA profile will use VOLTHA as the access technology. And then workflows run on top of profiles. And workflows are where the operator puts their business logic. So we have worked with AT&T, Turk Telekom, and Deutsche Telekom, and we are working on workflows for each of them. Today's tutorials will be using the AT&T workflow, just because we had to pick one of them to work with. But the whole key is that this is all modular, decomposable, and parts can be substituted out. So a different workflow just means swapping out one particular service that implements that workflow. And this is portable to many different operators. Now the NEM layer, it sort of crosses the software architecture layer. So the NEM will implement some parts down here in the platform. For example, XOS is an orchestration software that you'll be hearing about a lot today. And XOS will have services that run on top of XOS. Also part of the NEM will be the workflow and the logging and monitoring infrastructure. And we also have a bill of materials that will tell you if you want to build your SEBA pod, you know, these particular switches are known to work, these particular OLTs are known to work, these ONUs are known to work, etc. And we call this whole thing together a SEBA pod. So at our demos, we will have a couple of SEBA pods set up, and you'll be able to come over and see, here is the stack of hardware implementing a SEBA pod, and we will have a demo that walks you through a lot of the software running on the SEBA pod. And I think that concludes my section. I'm going to hand over to Andy, who is going to walk you through installing SEBA-in-a-Box.
So I'm Andy. I work at ONF. Let me ask, of the people here, how many of you intend to do the hands-on portion of the tutorial today? Good, good. I encourage you to do it. We'll give you a lab manual. It's mostly cutting and pasting from that manual and just seeing the output of commands. And I think you'll get a lot out of it in terms of really seeing what steps are involved to bring up SEBA and operate it and work with the hardware and so on. So that's good. I guess another question is, how many of you have experience with Kubernetes? Okay, yeah, pretty many. Since not everybody has worked with Kubernetes before, maybe we should just take a minute to walk through some of the basic concepts of the deployment of SEBA. And you'll see more of this today in the hands-on, but just give you a little bit of background. So a SEBA deployment consists of a bunch of microservices running on Kubernetes. So microservice architecture is simply a way to structure applications as a set of services that are modular. So you can swap them out for different ones that meet the same requirements. So SEBA is a collection of microservices running on Kubernetes. Kubernetes relies on Docker. So Docker is a way to deploy containerized applications. So Docker images package up all of the dependencies needed by the software, and a Docker container is a running image. So you can think of it as like a lightweight virtual machine. There are some differences, but I think at a high level, that's a good way to think about a Docker container. It's like a VM. So Kubernetes is an open source project that automates deployment of applications and also managing them and scaling them. So Kubernetes is built on top of Docker. It consists of clusters of one or more nodes. So we're going to deploy SEBA on a Kubernetes cluster consisting of a single node. But obviously, a cluster can have more than one node. So in Kubernetes terminology, a pod is a set of co-located Docker containers that always have to be running on the same node. So for the most part, a pod and a container you can think of as the same thing, but a pod can actually sometimes have multiple containers. A Kubernetes service represents the endpoint of an application. Like, how do you actually communicate with that application? An address and a port, for example. And a Kubernetes namespace is a partition of Kubernetes resources. So you can have each application, for example, could have its own namespace, and it's just a way to give a name to a group of components so that you can work with them. So the third tool that it's good to know something about for this lab is Helm. And Helm is a layer on top of Kubernetes, and it lets you deploy sets of Kubernetes resources. So Helm uses charts, and charts are basically a set of YAML files, YAML templates, that describe Kubernetes resources. So when you specify a Kubernetes resource, like for example, for setting up a pod or a service, then you'll give it a YAML file. Helm charts lets you group these YAML files together and put variables in them so you can parameterize them for different deployments. And Helm also, you can give it values files, which are YAML files that have the parameters in them that are used with the charts. Okay, so this is kind of dry, just some background. I think if you don't completely have this in mind, that's fine. You'll see it during the hands-on, and I think it'll start to make more sense. Okay. Excuse me for one sec.
Sorry.
Can you hear me? Can you hear me? Yep. All right, cool. All right. So this slide kind of summarizes how a SEBA deployment proceeds, and it's related to the last slide that Scott shows that showed the different layers of deploying the system, the platform layer, the profile layer, and the workflow. So when you deploy SEBA, you're deploying microservices on a Kubernetes cluster using Helm charts. We just went over that. The latest SEBA release is the 2.0 alpha release, and it's based on the Cord 7.0 release. Remember, SEBA is one of the projects kind of in this Cord family of use cases. And the way this proceeds is that you first install Cord platform charts, the base layer. So these are things like ONOS and Kafka and XOS Core. Scott already went over these. On top of that, we're going to install the profile charts. So these are VOLTHA, etcd is a key value store used by VOLTHA, a set of XOS services that are specific for the SEBA use case, and ONOS apps that are specific for SEBA. And then we install an operator-specific workflow chart. This is the subscriber logic that kind of ties together everything. And for the lab, we're going to be using XOS's ATT workflow driver service. So this is AT&T's subscriber logic. But this is modular. You could swap it in different modules for other operators. And then finally, so all of the installation to this point has been just generic, what you would do for any SEBA installation. Then you need to do some site-specific configuration for the specific hardware and topology that you're trying to manage with SEBA. And so TOSCA is a specification language that we typically use in SEBA for this. So those are the 4 steps: platform charts, profile charts, workflow chart, and then TOSCA. And you'll see that in the hands-on. Let me say just a couple of words about configuring SEBA using TOSCA. So we have an online guide at guide.opencore.org that has a lot of information related to what we'll be going over in this demo, and also related to operating physical SEBA installations. So I refer you to that. This particular page talks about all of the things that you need to configure to run a hardware SEBA pod. So you do things using TOSCA. You do things like configure the ports on your aggregation switch, tell it which port has the BNG, which port has the DHCP server. You configure technology profiles for configuring TCONS and GEM ports in the OLT and the ONU. You tell it where information about the OLTs, so for instance, the serial number, how VOLTHA can contact it, where it connects to the aggregation switch, so you're building out the topology. You configure information about ONUs, so for instance, what are the serial numbers of the valid ONUs in the system, where they live in the PON network, and that's used to construct a whitelist to make sure that OLTs are in the place that they should be. You configure bandwidth profiles for subscribers, so how much bandwidth each subscriber is allocated. And then you give other information about subscribers. So here, the abstraction of a subscriber is tying everything together. A subscriber maps onto an ONU with a particular serial number. A subscriber has the CNS, C and S tags associated with it for actually routing the traffic through the network. It has bandwidth profiles, technology profiles. Subscribers is the thing where everything comes together. So you need to use SEBA. You need to use TOSCA to configure this information into SEBA to actually operate the system. SEBA-in-a-Box is what we're going to set up in the lab. SEBA-in-a-Box is a virtual SEBA pod that you can use for SEBA development, for testing, for demos, just to understand what's there in SEBA. It uses virtual hardware. So the PONSIM module of VOLTHA virtualizes the PON network hardware, so the OLT and ONU, and it also provides a virtualized RG, residential gateway. And SEBA-in-a-Box uses Mininet to virtualize the aggregation switch and everything upstream from there. So the BNG, the DHCP server, is all implemented as virtual devices in Mininet. Some advantages of using SEBA-in-a-Box is it's fast to install. It can install in as little as about 10 minutes. And the reason that it can install so quickly is it's pulling pre-built Docker images down from Docker Hub and running them in Kubernetes. So using pre-built images, if you have a fast internet connection, you can get up and running quickly. It's easy to set up SEBA-in-a-Box. So the fast path is to download a repository from GitHub and run a make command, and it'll set up all of the layers for you, Docker, Kubernetes, and then on top of that deploy VOLTHA and ONOS and NEM and all the components of SEBA. So in the lab today, we're not going to be running make. We're going to kind of take the scenic route to get there and install each of the Helm charts individually so you can see this process of actually building up the system using these Helm charts. But just for your information, there's a faster way to get there. SEBA-in-a-Box is lightweight. So you can run it in a VM on your laptop. I regularly do that. You can run it in EC2. So if you wanted to run it, say, in EC2, then you can run it in a VM with pretty modest requirements. 8 gigs of RAM, 2 CPUs, that costs about 10 cents an hour. So it's pretty easy to get up and running with it. And it's also customizable, SEBA-in-a-Box. So it uses local copies of Helm charts, or you can use local copies of Helm charts and Docker images. So if you're doing development, you're trying to test out specific changes, it's easy to do that in this context. Okay. You can set up SEBA-in-a-Box with multiple virtual OLTs and ONUs. So it's possible to test different layouts of the PON network. We haven't really pushed the limits to see how many ONUs and subscribers that we could run in SEBA-in-a-Box. I have taken it to, I think, 4 OLTs, each with 16 ONUs, so 64, and that worked. But yeah, I don't know how it can really scale. But yeah, you can do more than just the extremely simple topology of 1 OLT and one ONU. But that's what we're doing in the lab today, just keeping it simple. Okay. So this slide has a lot of information on it. I'm not going to go through all of it, but the point of this slide is to convince you that when you set up SEBA-in-a-Box, you're setting up a data plane that looks a lot like the actual SEBA data plane running on real hardware, except everything is containerized and virtualized. So kind of walking from left to right. So the bottom level here is the actual data plane that SEBA-in-a-Box sets up. And these boxes are all containers running in Kubernetes. So we have an RG container, the residential gateway, and it connects upstream to an ONU container, separate container, and we connect these with a Linux bridge so that these can talk at layer 2. So in a real PON network, these would be connected with Ethernet. Here we're using Linux bridge. The ONU connects upstream to the OLT, right? So this is in this hardware pod. This would be where the PON network is between these two things. So here, these are connected with a gRPC tunnel, but this is where the PON network is emulated in this setup. OLT upstream connects to an aggregation switch, again using Ethernet. So we have another Linux bridge here, which allows for that Ethernet connectivity. And then the aggregation switch connects to a virtual host running in Mininet, which stands in for the BNG, emulates the BNG. So this is running a DHCP server. So what we're going to be able to do is send packets across this data path from the RG to the ONU, to the OLT, to the AG switch, and the BNG. That's the goal. Once we have this data plane set up, then VOLTHA and ONOS are running, and they are programming flows into this substrate, into the OLT and the ONU and the aggregation switch in order to set up the subscriber connectivity. So that's what the data plane looks like, and that's what we're going to set up.